Good morning students. In the last class we had solved some examples on capacitance calculation using Laplace's equation. Let us go through few more examples on the same topic. Consider this example. Find the potential function and the electric field intensity for the region between two concentric right circular cylinders where V is equal to 0 at R equal to 1 mm and V is equal to 150 volts at R equal to 20 mm if epsilon R is equal to 3.6. Find the surface charge density on each cylinder. Determine the capacitance between the conducting cylinders per meter length. So as asked to find the potential function, equation for the potential and the electric field intensity, and the region given is between two concentric right circular cylinders. Between two concentric right circular cylinders. Right circular cylinder is a cylinder in which there are two bases, the top base and the bottom base, right? The center of the top base and the center of the bottom base are connected. So this is the bottom base, this is the bottom base, and this is the bottom base, this is the top base. The center of the top base and the center of the bottom base are interconnected, right? And the radius is perpendicular to the surface. Radius of the right circular cylinder is perpendicular to the surface. That is what is the characteristics of the right circular cylinder. So two concentric right circular cylinders are there. That means the center of the two right circular cylinders is the same, right? The two concentric right circular cylinders, they have given boundary condition V is equal to 0 at R equal to 1 mm and potential equal to 150 volt at R equal to 20 mm. Epsilon R, that is relative permittivity in between the two circular cylinders, is 3.6. Find the surface charge density on each cylinder. You have to also find the surface charge density rho s. Determine the capacitance between the conducting cylinders per meter length, and the capacitance between conducting cylinders C should be calculated per meter length. Here, as it is a cylindrical surface, we have seen an example in our previous class on the coaxial cable, right, which acts as a cylinder, and if it is a cylinder, the potential varies only with R. Potential varies only with R, right? Potential varies only with R, and it is independent of phi and z. Hence Laplace equation for cylindrical system is del square V is equal to 0. So as it varies only with respect to R, right? In cylindrical system we have the coordinates R, phi and z. So 1 by R dou by dou R of R dou V by dou R is equal to 0. This is for del square V, right? Del square V for R coordinate is 1 by R dou by dou R of R dou V by dou R is equal to 0. If we integrate this, then we get R dou V by dou R is equal to C1, because if we are dou by dou R of R dou V by dou R is equal to 0, or if you integrate that, you get R dou V by dou R is equal to C1. That is dou V by dou R is equal to C1 by R. Dou V by dou R is equal to C1 by R. Again, if we integrate this, so what is our last equation? Our last equation is dou V by dou R is equal to C1 by R. Again, if we integrate this equation 1, we get V is equal to C1 ln R plus C2. C1 ln R plus C2. At R equal to 1 mm, V is equal to 0. So substitute these boundary conditions in this equation. We get 0 is equal to V is equal to 0. So 0 is equal to C1 ln R equal to 1 mm, 1 into 10 to minus 3 plus C2. At R equal to 20 mm, V is equal to 150. So substitute again the boundary conditions in this equation. We get 150 is equal to C1 ln 20 to 10 to minus 3 plus C2. If we solve these two equations, then we get C1 is equal to 50.1 and C2 is equal to that is 345.9. Put in equation 2. So these values you put in equation 2. So you get V is equal to 50.1 ln R plus 345.9 volts. Okay, right? In the last class I had explained how to solve the simultaneous equation. So if you want to solve the simultaneous equation, you have to put the Cal C in the mode, press the mode, right? Press the mode. Then equation is 1, 2 unknowns. We have 2 unknowns, right? So we have two equations. So first equation, what is our first equation we have? So first equation is at R is equal to 0 right? If you solve that, C1 ln 1 into 10 raised to minus 3, 0 is equal to C1 ln 1 into 10 raised to minus 3 plus C2. Okay, then that is our first equation. 150 is equal to C1 ln 20 into 10 raised to minus 3 plus C2. That is our second equation. So first let us see what is ln of 10 raised to minus 3. So ln of 10 raised to minus 3, it is minus 6.9077, minus 6.9077. okay, so it is minus 6.9077. then ln of 20 into 10 raised to minus 3, so write it 6.9077 we have here, minus 6.9077. then similarly for C1, 20 into 10 raised to minus 3, 20 into ln of 20 into 10 raised to minus 3. okay, so this will be minus 3.9. so one is 6.9, another one is 3.9. okay, so if you substitute this minus 6.9 and minus 3.9, okay, so that will be 6.9 and 1 is 3.9. okay, so what we have here, in keep it in equation mode, calci. so 1, number of unknowns 2, so first one is minus 6.9, then is equal to, this is 1, b coefficient is 1, then this is c is 0, a2 is minus 3.9, okay, then we have b2, that is 1, it is 1, c2 coefficient is 1, then it is 150 is equal to, so we get c1 is 50, then c2 is 345. okay, c1 is 50 and c2 is 345. so approximately c1 is 50.1 and c2 is 345.9. put these values in equation 2, we get v is equal to 50.1 ln r plus 345.9 volts. E is minus del v, so that is minus dou v by dou r of AR. only we get dou v by dou r because it is a function of r only, so minus dou by dou r of 50.1 ln r plus 345.9 AR bar. so if we differentiate this, we get 50.1 minus 50.1 into 1 by r, differentiation of 345.9 is 0. so it is E bar is equal to minus 50.1 divided by R AR bar volt per meter. so D is epsilon E. Right, this is our third step. so D is equal to epsilon naught into epsilon R into E bar. Substitute E bar here. so epsilon naught is 8.854 into 10 raised to minus 12 into epsilon R is 3.6 into 50.1 divided by R. so D bar is equal to minus 1.5969 divided by R AR bar nanocoulomb per meter square. Next step, on cylinders, dN bar is equal to rho s is equal to d bar, because only the surface charge density is equal to the normal component of flux density. The tangential component is 0 on the cylinders. so we have at r equal to 1 mm, rho s is equal to d bar, it is minus 1.5969, right, to 10 raised to minus 9 divided by r. R is 1 mm, 1 into 10 raised to minus 3, that will be 1.5969 microcoulomb per meter square. Then we have at R equal to 20 mm, rho s is equal to minus 1.5969, absolute value into 10 raised to minus 9 divided by 20 into 10 raised to minus 3, that will be 79.845 nanocoulomb per meter square. So next, fifth step is you have to integrate the surface charge density, because as it is surface charge density, you have to integrate 2 times. If it is a line integral, differentiate 1 time, surface integral, differentiate 2 times, integrate 2 times, and if it is a volume integral, you have to integrate 3 times. So here it is surface integral, so integrate 2 times. So and rho s is equal to dn is equal to d bar. So q is equal to integral z is equal to 0 and then phi is equal to 0 to 2 phi, right? Here when we were studying the cylindrical coordinate system, we have seen that if R is perpendicular, that is the differential surface area perpendicular to R is given by R d phi dz. In the first module when we are studying the cylindrical coordinate system, we have come across this, that is if the surface area is perpendicular to r. This is as it is a given surface is right circular cylinder which is perpendicular to r. So if it is perpendicular r, then the area is given by r d phi dz. So substitute this. So right, this will be our that is rho s. We have q is equal to rho s ds. So this will be ds r into d phi into dz. R and r will cancel. So we have only the limits from z is equal to 0 to z, because the z is nothing but the y, and that is our z axis, that is the axis of the cylinder, right? Z is the axis of the cylinder, so it varies from 0 to z, length of the cylinder. Then phi is the angle, it varies from 0 to 2 pi. So if this will be equal to 2 pi into 1.5969 into 10 to minus 9 into z. So that will be q is equal to, so if you are integrating here, different integration of d phi is phi, so it will be 2 pi minus 0, limit means 2 pi, then integration of dz is z. So this comes out to q is equal to 1.0036 into 10 to minus 8 z coulomb. Now we have to calculate for 1 meter length. So for 1 meter length, q is equal to 1.00336 into 10 to minus 8 into 1, z is 1, right? Now we know q, we know v, so substitute q and v in the equation c is equal to q by v. So if we substitute q and v, right, so before that we have to find the v value, right? V is equal to v at r equal to 20 mm minus v at r equal to 1 mm, because there is a potential difference. We should know the potential difference between the two cylinders, between two right circular cylinders. In between the area we are finding. So it will be 50.1 ln of 20 into 10 to minus 3 plus 345.9 after substituting C1, C2. Okay, so it is C1 ln r plus C2 what we have got. So substituting those values at r equal to 20 mm and r equal to 1 mm. So take the difference, that is v at r equal to 20 mm minus v at r equal to 1 mm. So if you solve this, you will get 50.1 into ln of 20 into 10 to minus 3, because 345.9 minus 345.9 will cancel, minus ln of 1 into 10 to minus 3. So that will be 150.0861 volts, or C is equal to Q by V. So substitute that, you get 66.8522 picofarad per meter. That is Q by V. Okay. Sorry, it is picofarad. It is a capacitance, so it is picofarad. 66.8522 picofarad. So this is how we have to solve if the given surface is a cylinder surface. Using Laplace equation, we are finding the value of capacitance. Next we will take one more example. In this example, find E bar at P of 3, 1, 2 for the field of two coaxial conducting cylinders, V equal to 50 volts at rho is equal to 2 meter and V is equal to 20 volts at rho is equal to 3 meter. So is asked to calculate the value of E, electric field intensity, at P of 3, 1, 2 for the field of two coaxial conducting cylinders. Again it's a coaxial conducting cylinders, right? So it is a cylinder what he has given, mentioned. So V is 50 at rho is equal to 2 and V is equal to 20 volts at rho is equal to 3 meters. So here he has given rho in cylindrical system. So rho is nothing but it is same as R. Sometimes in the convention they use R, phi and Z for cylindrical coordinates, or they use rho, phi and Z. So R and rho both are same. They use a cylindrical system and they are using rho. It is nothing but as good as R only. Right? So potential V does not vary with phi and Z, it varies only with R in cylindrical system or in coaxial cable, right? So 1 upon R dou by dou R of R dou V by dou R is equal to 0, del square V is equal to 0. So it is in cylindrical system. So 1 upon R dou by dou R of R dou V by dou R is equal to 0. So this is nothing but as he has used rho instead of R, so we let us use rho itself. So 1 by rho dou by dou rho of rho dou V by dou rho, right, that is equal to 0. If we integrate this, so we get dou by dou rho of rho dou V by dou rho is equal to 0, or rho dou V by dou rho is equal to integration of 0 plus C1, that is C1. So rho dou V by dou rho is equal to C1, or dou V by dou rho is equal to C1 by rho. Again if we integrate this, then we get V is equal to C1 ln rho plus C2. Now apply the given boundary conditions. Using the given conditions, V is equal to 50 volts at rho is equal to 2 meters. So that is 50 is equal to C1 ln 2 plus C2. V is equal to 20 volts at rho is equal to 3 meters. So 20 is equal to C1 ln of 3 plus C2. So we get 50 is equal to C1 ln 2 plus C2. That is 50 is equal to 0.6931 plus C2. 20 is equal to C1 ln of 3 plus C2, or 20 is equal to 1.0986 C1 plus C2. So if we solve these two equations simultaneously, then we get C1 is equal to minus 73.9827, C2 is equal to 101.2774. Now substitute this C1 and C2 in the equation for V. What is the equation for V we have got? So equation for V is C1 ln rho plus C2. We have got this after we have integrated 2 times, we have got V is equal to C1 ln rho plus C2. So in this equation, substitute C1 and C2, we get V is equal to minus 73.9827 ln rho plus 101.2774. E bar is equal to minus del V, right? This equation we are familiar. So minus dou V by dou rho of A rho, because V is a function of rho only, or V is a function of R only, is it not? So it will be minus dou V by dou rho of A rho bar. So minus dou by dou rho of minus 73.9827 ln rho plus 101.2774 A rho, right? So therefore E bar is equal to 73.9827 ln rho, differentiation is 1 by rho, so A rho volt per meter. Now this is in what coordinate system they have given? Cylindrical system. They have given the coordinates, that is at P of 3, 1, 2 in the given question, right? E bar at P of 3, 1, 2. So they have given the coordinates in Cartesian system. We have to convert it into cylindrical system. So conversion of Cartesian to cylindrical, rho is given by square root of x square plus y square, that is square root of 3 square plus 1 square, that will be root 10. So rho is equal to square root of x square plus y square. So E bar is equal to 73.9827 divided by rho. Rho is root 10, so that comes out to 23.4 volt per meter. So like this you have calculated the value of E for the field of two axial conducting cylinders, coaxial conducting cylinders, given the boundary conditions. So with these two examples, let us see few more examples in the second session of today's class. Thank you.